Hi, I'm Victor, and today we are going to be talking about Bayes' theorem. And now Bayes' theorem is based around probability, okay? And probability is a really useful tool that we've kind of came up with a mathematical tool to help update our guess on what the reality of the world is or a situation based on new information or prior knowledge. Now, to give you kind of a quick reason why we're talking about Bayes' theorem is eventually we're going to be using something called naive Bayes, and you can see why we call it, we're looking into this because it's going to be based on Bayes' theorem. But naive Bayes, which actually ends up being a supervised machine learning classification algorithm. A little bit of a mouthful, but basically we'll use this to classify different groups and figure out, which group we'll look into, say, like, for example, whether something is spam or not. And just, again, kind of quickly looking at what will be. This is a very fast and very relatively simple machine learning algorithm. And the reason why it's able to be so fast, it turns out to be based on this naive assumption, which ends up being to be related to that probabilities are independent. But we're not going to talk about that today. We'll get that into the future. But just kind of give you a heads up of why we're talking about Bayes' theorem. So Bayes' theorem based on probability. Probability, as you probably have some experience in your daily life. For example, the weather. When someone says there's a 10% chance of rain today, well, hopefully intuitively, say, well, okay, if I want to be prepared, I should bring an umbrella. But if I forget it for some reason or whatever, there's a pretty good chance that I won't have to worry about the rain, though there could be rain right now. And I think most people in the modern world understand the idea of probability for this small part. The one where it gets really tricky is when we have multiple probabilities and they start combining together. And that's actually where Bayes' theorem will end up giving us a mathematical formalism to help calculate the probability of these multiple situations, or using multiple conditions to figure out our situation and see how likely something is. And I said mathematical formalism. Mathematical formalism, what I really mean is essentially making an equation a way to formally approach the problem versus saying, like, if you didn't have it formally, you'll say, like, well, it's about this, or, like, I got a feeling it's this. The formalism helps clarify and helps us calculate exactly by how much we expect something to happen. All right. So first, we're just kind of going to drop into a scenario. It should be really familiar with people who are in the medical field. We're going to pretend we're going to go into the doctor, and we're going to be tested for the sickness that has that only occurs in about 0.1% of the population, which means that if we grabbed 1,000 people in the world, only about one in those 1,000 people will actually have that sickness, right? Versus, everyone else will be healthy. And it turns out we're going to be using a test which is 99% accurate, which actually has a little subtle point of what does that mean by 99% accurate. So this can actually be really important. In the real world, your test might be different depending on different parts of the population. It might be different depending if you are sick versus healthy. Maybe it's more accurate when people are sick versus less accurate when people are healthy. But in this case, we're going to just simply say that 99% accurate means that if you took 100 sick people, you would expect that 99 would be marked as correctly as sick, and unfortunately one person will be the test will say they're healthy, and we'll signify this with a positive for being sick and a negative for being healthy. Okay, so that's what we mean by 99% accurate for sick people. And then for healthy people, we had 100 healthy people. Very similarly, the 99 of the people will be marked correctly as being healthy, so negative. And one person will be unfortunately marked as being sick, even though they are in fact healthy. So they'll be marked as positive. Okay. So we get our news back from the doctor. We're like, okay, cool. We're sitting there. We're getting our test, and the doctor says, "Listen, you were marked as being positive for the sickness, but we want to do a follow-up test tomorrow to confirm whether or not you're sick. So we want you to go home, relax a little bit, and we'll confirm it tomorrow whether or not you're sick." And you might kind of go away from this meeting with her and say, "Oh, geez, like I don't feel sick. I mean, I don't feel like I'm sick, but oh my gosh, if 99% accurate, I'm probably sick, right? Right? Well, maybe not." So we're going to do some math to kind of help figure out what's the likelihood of us actually being sick, considering that we were tested positive? And I don't know about you guys, but sometimes math can make me feel a little more calm. That's my goal for you guys. So let's kind of draw some of this out. Let's make a fake scenario. So let's pretend we get 100,000 people randomly through the a population, and some people are sick, some people are not sick. So of those 100,000 people, how many would we expect to be sick? All right, good. We would expect, since it's 1% of the people would be, or 0.1% of the people would be sick, we would expect 100 people to in fact have, to be actually sick. And the rest of them, which turns out to be 99,900 people, will be healthy, not sick. Okay. And now what we're going to do, we're going to test all of them and give them the test and say, all right, are you sick or are you healthy? Either positive for sickness or negative for not being sick, meaning that the test thinks you're healthy. So let's start with the sick population. So we take those 100 people, and this is very similar to what we just saw, is 99% accurate, which means 99 people will be correctly identified as having a positive for the sickness, and one person will unfortunately be marked as negative, meaning that the test thinks they're not sick, but in fact they are sick. So it incorrectly guesses that. Okay. And then for healthy people, the 99,900 people, 99% of the time the test will show correctly that they are negative. They are not sick. And that ends up, if we do the math, ends up being 98,901 people will be shown as having, the test will show that they are healthy, and they are in fact healthy. And unfortunately, there will be 999 people, 1% of the time it'll guess incorrectly, and they'll be tested positive. So remember, in this case, we found that we tested positive for the sickness, right? So we are in one of two populations. We are either this population, the 99 people who are sick of those 100,000 people, or we are the 999 people of that 100,000 people who are healthy, and again, of people who are tested positive. So we actually don't have to consider this part because we didn't test negative, and we don't have to consider this population because we were, we didn't test negative, so we can actually just get rid of this so it's not too cluttery in our face right now. So we are either in one of these two populations, right? Because we tested positive. So let me ask you, which one do you think you would be? All right. If I said you tested positive, which one of these two populations do you think you'd likely be? And that's right. It turns out that we are likely to be in the healthy population. We are likely to be a healthy person that was just incorrectly identified as being positive for the sickness versus actually being sick and correctly identified being positive. So you might ask, like, wait a second, I thought the test was 99% accurate. Why so many people? Why are there more people who are healthy who tested positive? Well, the real reason comes down to the fact, well, anyone got a guess? All right. So good. So one of the reasons why, it turns out, it's just there's so many more healthy people. So there's just more chances for the test to guess incorrectly for all these healthy people versus this small population of 100 people here. So if we actually do the numbers quickly, we can actually say, okay, how many total people tested positive? Like for all the people who tested positive, and that turns out to be 999 plus 99. Those are the total number of people who were tested positive, right, for the test. And that ends up being about 1,098 people total. Okay. That's the total number of people who tested positive. And if we took the percentage now saying, well, of all the people who were tested positive, how many people were actually healthy? We would do 999 divided by 1,098, which I did some little math quickly before, turns out to be 91% of those people are actually healthy, even though they tested positive. And similarly, we can take this part right here, 99 people who were sick out of the 1,098 people who tested positive. It turns out that's only about 9% of those people who tested positive were actually sick. So we can actually see that we're likely to be healthy. Yay! We don't know yet, but hopefully we're part of this large portion of 91%. Hopefully that makes us feel a lot better. So quickly before we're going to take a break, and we'll talk about Bayes' theorem the mathematical formalism of how to write this, so we don't have to think of like 100,000 people. We can actually write this in more clear terms and more general terms in this formalism. Does anyone have any questions? Okay, good. All right, I do have a question over here. And they're saying, okay, we have two results for the test, but what if we had a third result? So maybe, that could possibly be it. Maybe, for example, this is a positive, or sorry, keep it. There's either a negative result, a positive result, and maybe there's something like, I don't know, like an at-risk result. So you're not sick, but maybe you're getting sick or something along those disease. You're at risk. In that case, we would have to have three different probabilities. So maybe the test would give us either at risk or negative or positive, and we'd have to have a third population here, right? That's not just healthy or sick, but also maybe at risk. But in that case, we would have to consider this whole scenario here with three different results, and we would have to say, at risk, negative, or positive. But once we have that, we would just look at just the people who are positive in this case. So we would get rid of everything else except for the ones that were positive, and we would add those part into our scenario. So that's a really good question. That's something we could maybe go a little bit further in when we do a Bayes theorem and how that would look like. But okay, so I think it's time for a break, and we'll come back together and we'll talk more about Bayes' theorem.